So the next speaker is the Rebecca Larson, who is talking about ions of reionization.
Thank you. Hi, I'm Rebecca Larson. I am finishing up my 5th year of my PhD at the University of Texas at Austin. And like Masami said, I'm going to be talking about a project called Islands of Reionization. I just want to give a shout out to all the people who have been part of this project. Thank you for all your work and your support and time. And if you have any questions going forward, please feel free to reach out to me. Because of the nature of this conference, I don't necessarily have to convince you why we study reionization. So we're going to just quickly talk about what part of reionization we're looking at. So we know that reionization ended around redshift 6. We don't exactly know when it started, maybe around redshift 15, but probably around redshift 10 or so, maybe 10% of the universe is ionized. And again, there's a lot of really great talks trying to narrow down some of these numbers. And so I just want to throw up the picture so that we, for completeness, have a picture of reionization. But I want to talk about how do we study galaxies themselves in the epoch of reionization, because it's a notoriously kind of one way to study the reionization process. Like, what are the sources that existed in the universe at that time? And so one of the ways we do this is looking for Lyman alpha. We can look for Lyman alpha in galaxies because it is attenuated by neutral IgM. So if you detect Lyman alpha, it's indication that you're in a ionized portion of the universe. And so if you look here, we show the fraction of Lyman alpha detected in Lyman bright galaxies as a function of redshift. And we would expect for it to continue to increase, but around redshift 7, it really drops off. I know there's a lot of updated plots, but this one is very dear to my heart because it's very clear that we're seeing a drop in the Lyman alpha fraction at redshift 7, and this could be due to the fact that there is more neutral IgM at that time that's attenuating this Lyman alpha. And so a lot of this is studied the beginning or the end of reionization. And what we wanted to look at was further into the epoch of reionization. Let's try to study galaxies that existed in the middle of this process. And so depending on what you expect and how this process kind of happened, we either expect reionization to happen a little bit delayed and then rapidly the universe became ionized, or maybe it was a slower process and it happened more gradually. Whether you need a large galaxy to emit a lot of radiation, and so you need time to build up a large galaxy, you have this gray curve here from Brandt's work, and in where you have big galaxies starting later but ionize the universe faster to meet up with our observations at redshift 6, or you have smaller galaxies with higher escape fractions that start the reionization process a little bit sooner, and it doesn't have to be quite so dramatic, and so it's more of a gradual reionization of the universe. And that's this blue curve here from Steve Finkelstein's work. And so what we wanted to do was target galaxies that are in this time frame where these two models are the most discrepant. And so redshift 9, either you have expected 10% of the universe ionized or 60 to 70% of the universe ionized. And if you're looking for Lyman alpha in galaxies, you want to find those galaxies that are in those ionized pockets so that the Lyman alpha isn't as attenuated by the IgM and you can detect it. And so what we looked for is we targeted a set of galaxies that were in the candles field that were photometrically selected to be at around redshift 9. We had great luck with the TAC at Keck, and so we had 8 nights over 4 semesters with this program, Islands of Reionization. We had J-band spectroscopy, and we had about 30 to so objects in our mass for each of our observations. And unfortunately, there aren't that many redshift 9 galaxies, so we have a target of 12 in our sample across these 4 candles fields, and then we filled the mass with some other targets, which Taylor Hutchison is going to talk about in a few minutes, and so stay tuned for that. But this is our observations. We were looking for Lyman alpha at redshift 8.5. To 10.1. And so, this is the J-band observations that we took. We encountered some problems that were already known, as you observe for long periods of time on the telescope, maybe it's not super accurate, and the objects themselves drift in your slits, and so we had to account for this. I'm not going to spend too much time focusing on the data reduction since I've given that talk before, but if you have specific questions or encountering similar problems, please feel free to reach out. It's been a long process of data reduction. The other thing that we did is after we accounted for this drift, we also incorporated the traditional MOSFIRE profile of an emission line where we have a triple Gaussian, where there are 2 negative traces and there is a positive trace for real detection. But we were also finding that our objects were offset from where the pipeline, the traditional MOSFIRE pipeline, was expecting them to be. So here I'm showing where at this black line right here is where the pipeline expected our object to be centered, but we're actually finding it centered here. And so if you are using an extraction profile that is not quite lined up with where your source is, you aren't getting the full flux, and you need to make sure that you're lining it up. And this is easy to do when you can see your object, such as this emission line here, and so you can tell the pipeline where you need to extract the center of your profile. But for our galaxies, we were observing over multiple nights, but we couldn't detect it in one night, just by looking by eye in the 2D of where you needed to use your extraction profile. And so what we ended up doing is using kind of a rolling extraction. So we found that none of ours were offset more than 3 pixels. And so we have an offset of -1 to +3 pixels of our extraction profiles, which I'm showing here, without knowing where our object was and needing multiple nights to get enough signal to stack together to see our galaxies. We needed to come up with a way of adding all of our observations together. And again, I'm not going to spend too much time on that because it was a whole long process and I want to focus on our results. We have an automated line finding routine that was from my 2018 paper where we look for emission lines in our data without any prior information using the MCMC chain. Again, I won't focus too much on that, so I'll just show our results. Here are all of the emission lines that we found in our data. And so I'm showing here the integrated signals noise of our emission lines on the x-axis and the sky RMS. So basically the error value on the y-axis here. And if you are to look at this plot, on the top left would be where skylines would be expected, and then the bottom right is kind of where you would expect real detections, where there's not a lot of error and you have high signals noise of your emission line. I'm showing all of our detections that we found. So like I said, our code is unbiased and it just does a search through all the wavelengths, but it's hard to kind of mask out the wings of skylines, and you're looking for very faint emission lines. And so trying to distinguish between these two things was a process of determining where we need to be making these cuts. We decided that sigma 5 seemed like a good indication of when we were expecting our emission line detections to be considered significant. And so you'll see that that's this vertical line here is anything above 5 sigma, we expect it to be more likely to be real. But we also did a negative test and contamination rates and things like that. So we find that our contamination rate is this horizontal line. So anything above that is not distinguishable from a contaminated or spurious detection or something like that. And so anything that falls in this bottom right part of the plot is what we would consider something that we want to take a look at or a real detection. I'm also coloring them based on the stacked. So we stacked all of our nights together and we have at least a 5 sigma detection in the stack of our data. But we also expect that if it's a real line that you would see it in your multiple observations. And so all of those that are colored in red are lines that are found at greater than 3 sigma in both of our nights of detection. And so we consider something to be real and not noise or a hot pixel or a very bright cosmic ray that wasn't reduced if we detected it more than one time. And so I will show you just the one observation and the one detection that we have. Unfortunately, I'm not as lucky as Ryan with a very high detection rate, but 1 out of 12 ain't so bad, especially at redshift 8.7. So here is our Lyman alpha emission line. Here is the postage stamps from Hubble and from Spitzer, and our photo Z was around 8.9, but our spectroscopic redshift is at 8.7. I'm showing the 2 nights of observation here in the 2 colors, and then the black is the stack, with the red being our emission line fit and our signal to noise in all of those detections. You can see in the stack 2D the positive and the 2 negative traces. And so I just want to show a little bit about this galaxy itself. It is the second brightest one in our sample. and we would expect to be seeing Lyman alpha potentially from the biggest and brightest sources, the easiest with the current technology that we have before JWST comes out. And so we have an equivalent with the Lyman alpha about 4.7 angstroms. I'm showing some of the properties we measured of a galaxy using Prospect or SED fitting, and here's some of the postage stamps again. And so what does this mean? We have a detection of Lyman alpha at redshift 8.7, and that's very exciting. But probably the more exciting part is that it's located physically really close to another object that's detected at that same redshift. And so if we actually look into our sample, we have what seems to be an overdensity by a factor of 5 of galaxies at redshift 8.7 in the EGS fields. And so we want to know how that has implications on reionization. And so we're going off of kind of the same thing that Ryan did, where we're measuring the ionized bubble size that could be created by these galaxies given their properties. And I'm showing what would happen if we had an escape fraction between 0 and 1. And even, if we have 100% escape fraction, we aren't always making a bubble big enough because we need at least a megaparsec for Lyman alpha to be transmitted. And so in order to see the Lyman alpha from these galaxies, you need to have a bubble big enough that's in that gray shaded area there. So we incorporated a luminosity function of all of the galaxies we'd expect that we wouldn't be detecting that would be in this megaparsec bubble size. And if we add up all of the flux from all of those, we still aren't getting enough ionizing radiation to produce a bubble, even 100% escape fraction, large enough that we would detect the detection that we have. But we need this overdensity factor. And so if we add in the 5 times overdense factor we have in this particular field, we would be able to see Lyman alpha from this galaxy because there's enough galaxies in the area that are producing ionizing radiation that's escaping, even at an escape fraction of something around 30%. And so if we change certain properties, we can do different things. Where we get a Sion value of 26, we could potentially also make a bubble this big if we had a higher escape fraction. And what's cool about this is these two properties are things that are going to be measured with JWST because this is in the EGS field, and this is where the Sears ERS program and some of our other data is going to be targeting. So we will be able to answer which one of these scenarios created this bubble such that we're seeing the Lyman alpha we're detecting. And so I will put up my summary slide here. I know I went through that really fast. So if there's any specific questions, please just let me know. And thank you.
All right, thank you, Rebecca. So time for questions.
So Janko asks, awesome work. Well, he's first. Awesome work on this great data. Looks like your redshift 8.7 Lyman alpha detection showed strong oxygen 3 in Spitzer, channel 2.
Yes.
Did your other candidates have similar Spitzer flux excesses?
Yes, this is actually part of our selection process for these galaxies. So in the photometry, we were selecting for those that had these red IRAC colors such that we would expect there to be high ionization parameters, also more likely to be in ionized bubbles this early on. So yes, that was intentional, and also kind of adds to the same picture of why we'd be detecting Lyman alpha in this galaxy.
All right. So, well, still the other people are writing up the questions. So, okay. Oh, okay. Rebecca Bowler is asking that, what is the error in your photometric redshift for the EGS source? Is the spec Z consistent?
Yeah, so here at the top right, we're showing the P of Zs for all 5 of these objects that are in our EGS field that are in our sample. And our spectroscopic redshifts, one for the Zitrin object at 8.683 and then ours at 8.661, both fall within our expected, pretty much kind of around the 1 to 2 sigma significance of our P of Z. And so, yes, our photo Zs are consistent with these 2 spec Zs.
So, any more questions via Slack? Right. Okay. Oh, yeah.
Yeah.
Christopher? Okay.
Yeah.
Go ahead.
Do you expect escape fractions of 30% at redshift 8?
I'm not quite sure that we could really put a measure on that, but we'll be able to to do a better job when we have more than just a Lyman alpha emission line. When we have J2T spectroscopy of this, and we can measure things like nebular emission, and that gives us kind of, some information about what's going on inside the galaxy. I would expect an escape fraction of 30% to be more likely than an escape fraction, in this range over here. But I will also caveat this was a pretty quick assumption and a pretty quick calculation where we weren't making escape fractions halo mass dependent, which we expect that to be the same, not the same escape fraction for all of the galaxies, which is what we did here in this calculation. And so when we have more information about the fainter galaxies that we're not detecting with Hubble, that we'll be able to see with J2ST, and when we have spectroscopic observations, we'll be able to make that kind of measurement. But here it was just a simple kind of case study on how possibly we could be making bubbles this big. Escape fractions of 30% for smaller galaxies seem not unreasonable.
All right. So it looks like time is up and many questions on the Slack. But yeah, let's move on. Let's thank Rebecca again.